All right, so now we're able to talk about, or we're ready to talk about, hopefully, the second type of improper integral. There's just the two kinds. The first one we did was the infinite integrand, or infinite interval. So we did the ones where the infinity was on the interval. So now we're going to do improper integrals where we have a discontinuous integrand. All right. So our outcome is I can determine if an improper integral of discontinuous integrand converges or diverges. So the last one was an infinite interval. So now we're going to do a discontinuous integrand, which you've never had this before. We never gave you problems that had this issue before. So you've never come in contact with this type of problem before. All right. So an improper integral of discontinuous integrand. That means our integrand has a discontinuity in it in our interval that we're going to do for the integral. All right, so that's a problem. So this first one, we can easily evaluate this definite integral. We can do the integral from 1 to 4 of this expression, 1 over x minus 5 squared. So here's the picture of 1 over x minus 5 squared. That is this expression, since it's squared, it has the two hyperbola pieces both concave up. And it has a vertical asymptote at 5. So there's a vertical asymptote right here. That's a 5 right there, if you can't see it as well. All right, so we have a vertical asymptote at 5. That's the graph of this picture. Now we are finding the area under this curve from 1 to 4. So we're going from 1 to 4. So 1 to 4. Not a problem. We can find that pink area. Not an issue at all. All right, but what if we try to find the area from 1 to 5? So what if we want the area under this curve going from 1 all the way over to 5 where this vertical asymptote is? This never touches the vertical asymptote. So what's the issue there? What's going to happen there? How can we find the area under the curve if the curve never touches this vertical asymptote? All right, and you never had that problem before in any other problem I gave you last year. Okay, so this is called an improper integral of discontinuous integrand. So we have a problem where we're discontinuing. We don't have continuity at 5 because there's an asymptote. All right, so that's the first type of issue we could have. We could also have this issue. Still a discontinuous integrand. Still the same topic. So I'm still doing 1 over x minus 5 squared. So here I'm still doing this same function, but now I want the pink area from 1 to 8. So I'm doing the integral from 1 to 8. I want the area under this curve from 1 to 8. There's an issue because there's a vertical asymptote at 5. So neither one of these curves actually connect and touch this vertical asymptote. So it could be that the area goes on forever up there, right? So again, we have a discontinuity in our interval that we got going on. So this is a discontinuous integrand. The integrand is the function, all right? So somewhere within the interval, our integrand, which is our function, has a discontinuity, has an issue, a hiccup, okay? And so that's what we got to deal with. So what are we going to do? All right, so these are the things we're going to do. So again, these are 3 different things, just like the last time. So we've got what's called a right-handed issue, a left-handed issue, and then we've got an issue in the middle, just like the picture I just showed you at the end. All right, so if we have an issue on the right-hand side, so if for some reason at B here, our function is not continuous at B, then we're going to do a limit and say that t approaches B from the left because you're approaching B from the left-hand side. So we're putting a t here, and we're going from A to B, so you're approaching B from the left-hand side. And then we've got the left-handed, which this seems backwards. I know this is a right hand because it's the right-handed side of the interval. Okay, this is a left hand. So this is the left side of the interval. So we're doing an integral from A to B, and for some reason there's a problem with our A value. Our A value is where the function is discontinuous. So we've got to replace that A with a t, and now we're going to say we're approaching A from the right side because we're approaching from this side. We're in the interval from t to B, so you've got to approach from the right side. Okay, and so I know that seems kind of backwards, but it'll make sense to you. Then what happens in the middle? Okay, what if you have a hiccup in the middle? Well, you've got to split this function where the hiccup is. So wherever the discontinuity is, you split it at that number into 2 integrals. Then you do the same thing as up here at the top with the left hand and the right hand integrands. you're gonna replace and put in place of this C, we're gonna approach it from the left, and then you're gonna put a T for this C and approach it from the right, because it's on the left side of the interval. So when you're in the interval from C to B, you're approaching it from the right side, even though it's the left side of the interval. And here it's the right side of the interval. Oh, and that should really be a T right there. Just haven't noticed that. All right, so you break this up, and we're going from A to T, so we've replaced our C with a T, and we're going to approach C from the left, and on this one, we've replaced our C with a T, and we're going to be approaching from the right. All right, so that's what we're going to do every time. So similar to the last time, but it's a little different concept. All right, so again, the words convergent and divergent. Convergent means we're going to get an answer. Divergent means we're not. All right, so let's just start with example number 1. I've just got 4 examples for us to do to just try to go through each one of these. All right, so for this first one, what is the hiccup or the issue that I have here? Well, secant is undefined at pi over 2, so this is an endpoint discontinuity. So what I'm going to do is I'm going to take the limit, and I'm going to let t go to pi over 2. So, and I have to go from, since it's going to be inside here, I'm going to be approaching from the left, so approaching pi over 2 from the left, and I'm going to replace that pi over 2 with a t. And that's all I've got to do so far. I've got to just replace the pi over 2 with a t, because secant x, if you try to put secant pi over 2 in the calculator, you're going to get an error. All right, so it has a discontinuity at pi over 2. So we have to replace the pi over 2 with a t, and we're going to approach that from the left side because that's the right-hand side of our interval. If that makes sense to you, hopefully. It's the right-handed side of our interval. So that means we're going to be approaching, figuring out the area under that as we approach that right-hand side of the interval from the left. Okay, so hopefully that makes sense. All right, so now we need our antiderivative. We're going to do the same thing we did last time. So I'm going to do the limit as t approaches pi over 2 from the left. And I need the antiderivative of secant x, which that's the natural log of secant plus tangent. That was one we had to memorize last year. So just go look in the back of the book, look in the flaps of your book, that the antiderivative of secant is the natural log of secant plus tan. And then we're going to evaluate that from 0 to t. So now I'm ready to do my fundamental theorem. So I've got the limit as t approaches pi over 2 from the left. So I'm going to do the fundamental theorem now. So I'm going to put a t in first. So this will be the natural log of secant of t plus tangent of t. And then it's minus the natural log of secant of 0 plus tangent of 0. So all I did is I plug a t in first, subtract, and then I plug a 0 in. So now we just got to figure out this answer. Let's simplify what we can on the inside. All right, so over here you can't simplify anything yet until you take your limit. Over here we can simplify both of these guys. So what is the secant of 0? All right, the secant of 0, you got to think on the unit circle. Well, I'll write under here. All right, we got to think on our unit circle at 0 right here, which is 1, 0. What is your secant value? Your secant value is your reciprocal of cosine. Remember, this is cosine and sine. So your secant of 0, this is 0 on the unit circle, 0 pi over 2 pi. Okay, so I'm at 0 on the unit circle. I'm at the coordinates 1, 0. I want the secant. The secant is the reciprocal of cosine, so that's going to be 1. Now I want the tangent at 0. The tangent is sine over cosine, so that would be 0 over 1, so that's 0. Now 1 plus 0 is 1, so the natural log of 1, that is 0. So the secant of 0 gave us an answer of 1. The tangent of 0 gave us an answer of 0. Then you have to add them together. 1 plus 0 gives you 1. And then you're doing the ln, the natural log. I'll put the bars just to keep the bars there, not that I need them. Is the natural log of 1. Well, we know the natural log of 1 goes to 0. That value is 0. So really all I have is this over here. Okay, so I've got the limit as t approaches pi over 2 from the left of the natural log of secant t plus tangent t. That's all I got. So I've got to evaluate what this equals. Okay. So think about what secant looks like and what the tangent curve looks like. All right, well, let's just take a look. What does the tangent curve look like? This, right? The tangent curve looks like that. Okay, so if we approach pi over 2, here's pi over 2. If you approach pi over 2 from the left-hand side, coming from the left, what is tangent doing? Tangent's going to infinity. Okay? And if you know what the secant curve looks like, the secant curve, here's cosine. All right, that's the cosine curve. Secant curve is just flipped out of that. It's just a flipped out of that. It's just take that curve and flip it out. That's what you studied when you studied pre-calc. That these guys are taken out like this and flipped out. All right, so here again, this is pi over 2. So what is the secant doing? All right, when we put in pi over 2, what's the secant of pi over 2 as we approach from the left-hand side? It's also going to infinity. So this has ended up being infinity plus infinity. Okay, we can do infinity plus infinity. We can't do infinity minus infinity, so don't get confused with that. We can do infinity plus infinity. So then this is giving us an infinity answer. So what is the natural log of infinity? So think about what natural log is doing. Remember, natural log is doing this. All right. So as x goes to infinity, what's our y value doing for the natural log? It's going to infinity. So this answer is d and e. So this diverges. And I know that's multi-step. That's a million gazillion steps. But you just got to take your time and think through it. So the first thing I did was I thought through what each one of these were when I put in pi over 2. So the secant of pi over 2 from the left, it was going to infinity. The tangent of pi over 2 coming from the left, the tangent was also going to infinity. So I have infinity plus infinity, which is infinity. So then I'm thinking about, okay, what's the natural log of infinity? Well, then I'm thinking about the curve for natural log. As x goes to infinity, what's my y-coordinate doing? Going to infinity. So this is a D and E situation. So this is a divergent problem. All right. So it's a lot of multi-steps. I totally get it. It's going to take a while for this to sink in. It really is going to take a while. All right. And this is the last thing we're doing. This is the end of it. All right. For the semester. All right. Determine whether the integral is convergent or divergent. Oh, I didn't change the problem. All right. So let's try this one. So we're going to do the same thing. I think about what's going on here in this problem. So what is the issue with this expression on the interval from 2 to 5? Well, if you look down here in my denominator, can x be 2? And the answer is no, because that's going to give you 0 in the denominator, right? So there's an issue here with this end of our interval. So what we're going to do is we're going to do the limit and let t go to 2, but this time we got to come from the right, 2 from the right. And then we're going to replace that with a t. So this is the problem we've got to evaluate now. All right. So I replace the 2 with a t. And we're going to take the limit and let t approach 2 from the right because it's the left side of our interval. So we're going to be approaching that, getting that area as we get closer to 2 coming from the right, since it's the left-hand side of our integral. Our interval. All right, now we got to rewrite this here, the limit as t goes to 2 from the right side. So now I need the antiderivative of this expression, and then I'm going to evaluate it from t to 5. Okay? So what is the antiderivative of 1 over the square root of x minus 2? All right, so let's rewrite this. Let's just do a little scratch work up here. So if I rewrite this problem, that's really x minus 2 raised to the negative 1/2, right? Because this is a square root sign and it's in the denominator. So this is x minus 2 to the negative 1/2. So now I want his antiderivative. So what do you do to find an antiderivative? You add 1. So that's going to be x minus 2 to the positive 1/2 because I'm adding 1. And then I divide by my new power or multiply by the reciprocal, right? So there's my antiderivative. 2 times x minus 2 to the 1/2. There's my antiderivative. So now we're going to do the fundamental theorem. So we're going to do the limit as t approaches 2 from the right side. and we're going to do the fundamental theorem. So I'm going to put a 5 in first. So that'll be 2, 5 minus 2 to the 1/2 minus, now let's put t in here, 2 to the t minus 2 to the 1/2. So I did the fundamental theorem, right? So I put a 5 in first, minus, and then I put a t in. All right, so let's think about what's going to happen here. This first part, this is just going to give me 3 to the 1/2 times 2. I'm getting a number answer for this. And so that'll be a limit of a number is going to be a number. So far, this part is just a number, 2, and then it'll be the square root of 30, because that'll be 3 to the 1/2. All right, so now what's going to happen on this part? Well, if we have this approach 2 from the right-hand side, if you approach 2 from the right-hand side, this expression is the square root of t minus 2, which is this expression, the square root of t minus 2. And so that's this where it hits 2 on the, that's the graph of that function. That's the square root, move 2 to the right, right? Square root of x, move 2 to the right, because we know what square root of x looks like, move it to the right. So if we approach 2 from the right, what's your y-coordinate doing? Your y-coordinate's approaching 0. So this is going to go to 0. Plus, if you just plug a 2 in here, you get a 0. 2 minus 2 is 0. So this will be 2 radical 3 plus 0. So the answer is 2 radical 3. So this converges. I actually got an answer. 2 radical 3. Boom, done. That one doesn't seem as complicated as the other one because it wasn't any trig stuff. All right. So again, we just replaced the 2 because that's where the hiccup was with a t. We did our limit and approached 2 from the right since it's the left side of the interval. We did the antiderivative, then we did the fundamental theorem, and then we just evaluated and see if we get an answer or not. That's all you're doing every single time. All right, so let's look at number 3. This one says to choose C as 1, so I kind of helped us out. So why am I having to choose C as 1 here? Well, the issue is here, this expression, which I could keep the dx, I could write the dx over here and just have this be 1 over x minus 1, if that bothers you having the dx up there at the top. Okay, the issue with this function, 1 over x minus 1, is that it is undefined when x is 1. Because if you put a 1 in here, you get 0 in the denominator. So 1 is in the interval between 0 and 3. So this means this is not continuous within this interval. So that's why we have to choose C to be 1, because that's where the hiccup is, okay? So what we're going to first do is we're going to rewrite this as 0 to 1 of 1 over x minus 1 dx plus 1 to 3 of 1 over x minus 1 dx, okay? So we had to split it up where the problem child is first. Now, you've got to take each one of these and do a left-sided or a right-sided limit because you can't equal 1 either. So 1 cannot be your endpoint. So this one, we're going to have to take the limit and let t approach 1 from the left and replace that with a t. And then on this one, I can't have 1 either as an endpoint because when you put 1 in here, it's going to blow up. So I can't have 1 in there, so I have to replace that as well. So I'm going to let t approach 1 from the right side because this is the left-hand side of my limit, so I have to approach it from the right side. And then put a t here, t to 3 of 1 over x minus 1 dx. All right, so now I've done that. I've replaced my problem childs with the correct limit values, okay? So now we're ready to do our antiderivative. So what is the antiderivative of 1 over x minus 1? That should be an easy one for you. All right, we're doing the limit as t approaches 1 from the left. My antiderivative of 1 over x minus 1 is the natural log of x minus 1. And then I'm evaluating that from 0 to t. Okay, and over here we'll do the same thing. A limit as t approaches 1 from the right. I'm doing the antiderivative of 1 over x minus 1, which is the natural log of the absolute value of x minus 1. I'm evaluating that from t to 3. All right, so now, tired of red again, so I'm switching to blue. So now we're ready to do the fundamental theorem. All right, so I'm going to do the limit as t approaches 1 from the left. I'm going to do the fundamental theorem here, right? Okay, I could have had brackets there too if I wanted them. Okay, So we're going to do the fundamental theorem. So this is going to be the natural log of t minus 1. And then we're going to subtract, putting in a 0 in here. So if you put a 0 in here, that's going to be 0 minus 1, which is negative 1, and the absolute value of that is 1. So that would be the natural log of 1. So that's that one. And then we're going to do the limit as t approaches 1 from the right. We're going to do the fundamental theorem here. So I'm going to plug a 3 in. So that would be the natural log of 3 minus 1 will be 2. And then minus, now we put a t in here, natural log of t minus 1. P minus 1. All right, so there we go. So now we got to think about what's going on here for each one of these. Okay, what is happening with each one of these answers? Okay, well, we know that the natural log of 1, that's 0. Okay, so that's gone. Over here, natural log of 2, that's just a number, natural log of 2. So this one's got a number in it over here. Over here, we got 0. That's gone. So now I got to think what's happening to this function right here as we approach 1 from the left-hand side.